Unstructured data arrays are expanding exponentially across modern corporate networks, yet most enterprises remain completely blind to the underlying geometric relationships hidden deep within their siloed legacy production databases. Without clear mathematical maps, traditional search queries suffer from severe latency bottlenecks, producing highly inaccurate similarity matches that drain your software analytics compute budgets month after month. This infrastructure crisis forces engineering teams to rely on primitive, slow lookups, dragging down operational efficiency and stalling the deployment of real-time intelligence across the entire enterprise ecosystem. To solve this computational bottleneck, data architects are abandoning brute force database searches and turning to foundational statistical frameworks that map complex relational structures directly into unified spaces. According to rigorous mathematical optimization research conducted by the Riken Center for Advanced Intelligence Project, high-dimensional spaces provide the clean geometric separation necessary to categorize complex corporate datasets. By shifting from localized data tables to comprehensive spatial frameworks, organizations can unlock hidden relational patterns, transforming disorganized corporate data into clean, structured assets ready for immediate analysis. The core mechanism enabling this architectural evolution is the support vector machine, a powerful mathematical framework designed to handle high-dimensional classification challenges with absolute structural precision. Rather than analyzing data points in their raw, lower-dimensional state, this methodology projects unstructured information into an expanded vector field, where hidden linear boundaries can be discovered. This spatial projection allows complex, non-linear relationships to become perfectly separable, establishing a robust foundation for automated decision-making engines across high-throughput enterprise software platforms globally. By establishing clear geometric relationship maps, large-scale systems can eliminate messy computational guesswork, ensuring that every single query returns precise, mathematically verified classifications at optimal speeds. To project this data without triggering a complete memory bottleneck, architects utilize sophisticated mathematical tools known as kernel functions to calculate high-dimensional inner products very efficiently. The famous kernel trick bypasses the need to explicitly compute coordinates in vast spaces, drastically reducing the hardware overhead required to process multi-terabyte corporate data arrays. By evaluating similarity metrics directly within the original space, these specialized functions deliver the computational power of infinite dimensional mapping while maintaining a highly stable system memory footprint. Whether deploying radial basis functions or polynomial kernels, choosing the correct mathematical metric determines how accurately your infrastructure can isolate critical operational signals from noisy corporate data. This precise spatial positioning creates an optimized environment for discovering the maximum margin hyperplane, which acts as the definitive boundary line separating distinct enterprise data categories. The primary objective of the support vector machine algorithm is to maximize this geometric distance between the hyperplane and the closest training data points, known as support vectors. By maximizing this margin, the system guarantees the highest possible generalization accuracy, preventing the common architectural failure of overfitting when encountering entirely new production data streams. These critical support vectors carry the entire structural weight of the classification model, allowing engineers to completely discard redundant data points and streamline downstream inference operations significantly. This sparse mathematical reliance ensures that once the model is fully trained, the runtime execution requires minimal processing power, making it ideal for low-latency enterprise search applications. As a direct result, massive data arrays can be queried continuously without experiencing the performance degradation typical of legacy relational database systems under heavy multi-tenant operational loads. Implementing these advanced statistical modeling frameworks drives a profound macroeconomic shift. systematically slashing enterprise software analytics compute budgets through the utilization of global optimization formulas. Empirical data compiled in the Stanford Human-Centered AI Index confirms that shifting to mathematically optimized data structures drastically reduces the long-term hardware capital expenditures of industrial organizations. By eliminating redundant cloud compute cycles, enterprises can reallocate critical financial resources away from basic infrastructure maintenance and directly toward high-impact algorithmic research and development initiatives. This economic optimization fundamentally alters the internal corporate labor force, rapidly advancing basic script runners into highly specialized data scientists capable of engineering complex vector topologies. As simple automated pipelines absorb routine coding tasks, technical teams must master advanced concepts like non-Euclidean clustering, Mercer's theorem, and high-dimensional regularization parameters to remain competitive. The International Labor Organization Future of Work Index highlights that this rapid upskilling trend is reshaping global employment metrics, driving intense demand for elite mathematical engineering talent. Organizations that proactively invest in training their workforce to manage these spatial high-dimensional systems achieve significantly higher productivity gains compared to those relying on legacy transactional processing. This evolution turns the IT department from an expensive operational cost center into a powerful engine of corporate innovation, directly accelerating the pace of broader digital transformation. However, transitioning to these high-dimensional vector spaces requires a strict multi-stage deployment lifecycle that begins with meticulous data preparation across all legacy corporate information repositories. Before running complex kernel metrics, engineering teams must completely clean and transform disorganized enterprise data arrays, eliminating missing values and normalizing variable scales across every silo. Because support vector machines are highly sensitive to variable scaling, failing to normalize input vectors will distort the geometric distance calculations, completely ruining the accuracy of the hyperplane. Architects must implement automated data ingestion pipelines that handle parsing, tokenization, and scaling transformations seamlessly, utilizing robust frameworks validated by enterprise orchestration leaders like Llama Index. Once the data layer is thoroughly prepared, the technical team can initiate the optimization process, solving the dual quadratic programming problem to identify the absolute global maximum. Unlike deep neural networks that often get trapped in localized minima, the convex optimization landscape of support vector machines guarantees a unique, globally optimal solution every time. This mathematical certainty provides enterprise architects with unparalleled system predictability, ensuring that model behavior remains perfectly consistent across diverse, high-volume production software environments. After converging on the optimal hyperplane parameters, the model must undergo rigorous validation testing using enterprise benchmarks designed to monitor downstream performance shifts and track potential degradation matrices. By cross-examining model outputs against standardized datasets from the Vector Institute, engineers can accurately measure classification accuracy, precision, and recall scores before authorizing full production release. This strict validation protocol prevents context drift and ensures that the statistical model can handle real-world operational variance without experiencing sudden, catastrophic accuracy drops in the field. Once validated, the model is compiled into an optimized execution graph, allowing it to run natively across variable hardware chip topologies using cross-platform runtimes like the ONNX engine. This deployment strategy decouples the analytical logic from specific underlying server drivers, enabling seamless scalability across hybrid cloud environments and bare metal edge computing infrastructure architectures. Looking toward the future of data architecture, spatial high-dimensional clustering serves as the absolute technical foundation for modern vector search capabilities across the global tech sector. The geometric principles established by support vector machines directly inspire the indexing and management methodologies used to navigate billions of high-dimensional embeddings within modern production databases. By mastering vector space projection, enterprises lay the groundwork for building advanced retrieval-augmented generation networks that feed highly accurate contextual data straight into large language models. Technical specifications published by Pinecone Vector Database highlight that managing these massive vector fields with ultra-low latency requires continuous innovation in spatial indexing algorithms and memory management. As corporate knowledge graphs grow increasingly complex, decoupling analytical logic from internal neural network weights becomes essential for maintaining strict compliance, data governance, and systemic security. By integrating semantic metadata schemas defined by the W3C semantic web activity, organizations can build hybrid architectures that combine rigid symbolic logic with flexible vector similarity scoring. This powerful combination allows enterprises to control AI outputs with extreme precision, virtually eliminating the risk of destructive hallucinations while maintaining high conversational agility across user applications. Furthermore, establishing secure tool-calling communication channels between these high-dimensional data repositories and external AI hosts requires the strict implementation of open standard protocols like the Model Context Protocol. By ensuring stateless, fully authenticated database interactions, enterprises can confidently scale their multi-agent routing clusters without exposing sensitive underlying corporate intellectual property to unauthorized access vectors. This systemic security focus is paramount, as detailed by the OWASP Foundation, which mandates strict data isolation controls and runtime execution limits for all production enterprise intelligence systems. The historical transition from basic script running to advanced empirical statistical modeling highlights a permanent shift toward mathematical rigor and structural discipline across the global corporate technology landscape. Enterprises that embrace high-dimensional vector spaces today are building the core infrastructure that will power the autonomous, agentic enterprise systems of tomorrow with unparalleled computational efficiency. By anchoring your data strategy in clean geometric relationship maps, you eliminate the severe operational risks of data fragmentation and unlock the full potential of your corporate intelligence. The math is absolutely clear. Maximizing classification margins within optimized vector fields is the single most effective path toward achieving predictable, high-performance enterprise analytics at scale. As scaling laws challenge traditional compute limits, the efficiency of sparse mathematical optimization models ensures your infrastructure remains sustainable, secure, and ready for future architectural breakthroughs. Do not let your critical data assets remain trapped in disorganized legacy transactional silos that drain your IT budgets and slow down your organization's decision-making velocity. Partner with elite engineering teams, implement robust data normalization pipelines, and deploy advanced spatial clustering frameworks to transform your enterprise architecture into an unassailable competitive advantage. The blueprint for high-dimensional enterprise intelligence is already here, combining deep mathematical precision with practical, risk-adjusted deployment life cycles engineered to deliver maximum operational value. Take complete control of your technical infrastructure today by moving past the superficial industry hype and anchoring your development strategy in proven, mathematically sound data science principles. Stop guessing your tech strategy and wasting your time. Subscribe to Enterprise Tech Brief right now. We deliver zero-hype, pure architecture, the blueprint of enterprise intelligence. Completely free. Hit the subscribe button